Hey, fasten your seatbelts. Here comes the world's fastest review of trigonometry. Trigonometry, all wrapped up in this thing called the unit circle, which is the circle centered at the origin with radius 1. That's the unit part, radius 1. In other words, this point here is 1, 0. This point here is 0, 1, etc. In trigonometry, we talk about angles, often called theta, just a Greek letter. You could call it what you like. And what we're talking about is the angle that some ray makes when you go counterclockwise from the positive x-axis to that ray. So that's the angle that I've drawn here as the angle theta. In calculus, we never measure these angles in the degrees that you are used to. Instead, we use this unit called radians. And the radian measure of an angle is nothing more or less than the portion of the circumference of the unit circle that it carves out. Subtends is the actual mathematical word, but we're talking about the distance along the unit circle right there, the part of the circumference that we use up right there. That's the measure of this angle theta. Now you probably remember that the circumference of any circle is 2 pi times the radius. And since this is the unit circle, it has a radius of 1, and so its circumference is 2 pi. And that tells us that the angle that goes all the way around the circle from the beginning to the end, well, that maps out the radian measure of the entire circumference of the circle right there, or a radian measure of 2 pi. In other words, what we normally think of as 360 degrees, or once around the circle, is 2 pi radians. And from that, dividing by 2, you get that 180 degrees is pi radians. And a little bit of extra arithmetic gives you these other common values. A 90-degree angle is pi over 2 radians. A 45-degree angle is pi over 4 radians. 60 degrees is pi over 3 radians. And 30 degrees, pi over 6 radians. If you look at where the angle theta intersects the unit circle, that point, like any other point in the plane, has x and y coordinates. Those x and y coordinates are completely dependent on the angle theta, and so we call them cosine of theta and sine of theta. I'll say it again. All that cosine of theta is the x coordinate of where the angle intersects the unit circle. All the sine of theta is the y coordinate of where the angle intersects the unit circle. So that, for example, I could ask you now, what's the sine of pi over 2? Well, pi over 2 is 90 degrees, or you could think of it as a quarter of a way around the circle, because the full way around the circle is 2 pi. And so we're talking about this angle right here. Sorry for drawing it so sloppy. And we're talking about this is the point where it intersects the unit circle, and the sine is just the y coordinate, and so the sine of pi over 2 is 1. And by the same logic, the cosine of pi over 2 is the x-coordinate of the point where the angle pi over 2 meets the unit circle, and the x-coordinate there is 0, because the coordinates of that point are 0, 1. And so the cosine of pi over 2 is 0. You should now be able to answer questions like, what is the sine of pi? Well, pi is this angle here, halfway around the circle. We're talking about the y value of that point right there, and so the sine of pi is 0. What's the cosine of 5 pi? Well, 5 pi is this angle here. Here's 2 pi once around the circle, and then you have to go another pi, and so you end up right there again. And so we're still talking about this angle right here, and so the cosine of 5 pi is the x value of that point right there, which is -1. Similarly, what's the sine of negative pi over 2? Well, if pi over 2 is the angle when we go that way, pi over 2, clockwise, quarter of the way around the circle, negative pi over 2 means going counterclockwise the same distance. And so we're talking about this angle right here. That's the angle negative pi over 2 from there to there. And if we're looking for the sine of that angle, we're talking about the y coordinate of this point, and that's -1. And it turns out there are a bunch of these sines and cosines of common angles, at least in the first quadrant, that you simply have to know. It's not hard to remember that the cosine of 0 is 1. That's the x coordinate of the 0-degree angle, so that's easy. And by the same token, the cosine of pi over 2 is 0 because that's the x coordinate of a 90-degree angle. Similarly, the sine of 0 is 0 and the sine of pi over 2 is 1, so you could probably figure those out. And then there's a bunch of other ones that you simply memorize. You need to know these. They have to come quickly to you. If you really needed to, there's a trick for figuring them out once you know the first couple, the ones and the zeros. And the trick is just this. You can think of them as square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2 in order. When you simplify, you get exactly the right answers. Better to have it simply at the tip of your tongue and easy to write down without thinking about it. On the other hand, if it's not right there, better to get it right. It's worth noting, and will sometimes be important, that the sine and the cosine are always values between -1 and 1 because they are x and y values on the unit circle, and so they have to be between -1 and 1. And then the sine and cosine are only 2 of the 6 elementary trigonometric functions. The other 4 are defined in terms of the sine and cosine. We define the tangent of theta as the sine of theta divided by the cosine of theta, the cotangent of theta as the cosine of theta divided by the sine of theta, the secant of theta as 1 over the cosine of theta, and the cosecant of theta as 1 over the sine of theta. And I'm with you that that's very confusing. In particular, you would love it if the cosecant of theta was 1 over the cosine of theta, but that is simply not the way it works. The way I remember it is, it's all messed up. So sorry, mathematicians are sadists. This is the way it's defined. That's the way you have to remember it. It's also worth noting that the trigonometric functions are all periodic, meaning they repeat. How come? Because the circle repeats. Add 2 pi to any angle theta, and you get right back where you were to the same angle theta. Which is to say, for example, that the sine of theta plus 2n times pi, where n is some integer, is just the same thing as the sine of theta. If you add 6 pi or 200 pi or -200 pi to whatever angle you have, you get the same angle, and so it has the same sign. You should probably have an idea of what at least some of these functions look like, but since this is supposed to be a blazingly fast trigonometric review, we'll skip that for now. But it is worth noting that the sine and the cosine, defined for all real numbers. Every real number has a sine and the cosine. Not so for any of the other 4 elementary trigonometric functions, because they all have these denominators that could be 0. So, for example, any place where the cosine of theta is 0, the tangent of theta is undefined because you're not allowed to divide by 0. So, for example, tangent of theta undefined at pi over 2, and at -pi over 2, and at 3 pi over 2, and at infinitely many other places. And so these other 4 trigonometric functions, in a sense, horrible functions compared to the sine and cosine, which are defined everywhere. Okay, trigonometry is full of these things called identities, which are equations that are always true. And the most famous and probably most important of these is that sine squared theta plus cosine squared theta is equal to 1. And I am going to bother to briefly show you where that comes from, but first we should talk about the notation a little bit. And first of all, sine theta, written as it is on the left here, is just notation for sine of theta, where we tend to often leave out the parentheses because it's shorthand and we write it so often that we want to abbreviate. But the sine is a function and you have to take the sine of something. And so it means sine of theta, whether or not you have the parentheses there. There's no multiplication going on. Sometimes people get confused and they think this is sine times theta. That doesn't make any sense. This is the sine of some angle theta, meaning what's the y coordinate of where that angle intersects the unit circle. And then this notation sine squared theta, that's just notation for the sine of theta all squared. And the reason we have that notation is, what if we just tried to write it as sine of theta squared, like I just did here in orange? Well, what does that mean? Does that mean you take the sine of theta and then square the result? Or does it mean you square theta and take the sine of the result? The answer is, who knows? And so if you're trying to say that you want to take the sine of theta and square the result, then we write it like this, sine squared theta. If you really wanted to square theta first, you'd write sine of theta squared like that, which is usually not what you want. Okay, I promised to show you briefly where sine squared theta plus cosine squared theta equals 1 comes from. It comes from the unit circle, at least to start. That should be no surprise. You find some angle theta. It intersects the unit circle at the point cosine theta sine theta. And you can see that gives us a right triangle whose bottom side has length cosine theta and whose vertical side has length sine theta, and whose hypotenuse is 1. How do I know the hypotenuse is 1? Is because it's the unit circle, the circle with radius 1, and the hypotenuse of this triangle is a radius of the circle, so it has length 1. And so sine squared theta plus cosine squared theta equals 1 squared, which is just 1, is just the Pythagorean theorem applied in this particular case to the unit circle. So sine squared theta plus cosine squared theta equals 1, the most important trigonometric identity. Dividing both sides of this identity by cosine squared theta gives you this version of it, tangent squared theta plus 1 equals secant squared theta. And dividing the original identity sine squared theta plus cosine squared theta equals 1 by sine squared theta on both sides gives us 1 plus the cotangent squared theta is equal to the cosecant squared theta. So sometimes those identities are useful as well. You can also see from the picture on the right that if we start with some angle theta that's going in the counterclockwise direction, and we look at the angle negative theta, which is the same angle but going clockwise instead, then that angle intersects the unit circle at the same x value, so has the same cosine, but at the proportional same y value, but in the other direction. In other words, it has the negative of the sine of the original angle. Which is to say that the cosine of negative theta is just the cosine of theta, but the sine of negative theta is the negative sine of theta. So here are 2 more trigonometric identities. There are tons of trigonometric identities, but only a few more that we're going to need for now. And the first is this, that the cosine of the sum of 2 angles, the cosine of x plus y, is the cosine of x times the cosine of y minus the sine of x times the sine of y. And you'll often see this one in the special case where x and y are the same angle, so that x plus x is 2x, and it simplifies to the cosine of 2x is cosine squared x minus sine squared x. Similarly, there's an important trigonometric identity for the sine of x plus y. It's sine x cosine y plus cosine x sine y. And as with the cosine, you often see this in the version where x and y are the same angle and get the sine of 2x, which simplifies to 2 sine x cosine x. Personally, I find these 2 more general formulas difficult to remember, and yet these special versions very simple to remember. And so what I do is I remember cosine of 2x is cosine squared x minus sine squared x, and sine of 2x is 2 sine x cosine x, and then I work backwards and try to say, well, what could the formula for cosine of x plus y, sine of x plus y have been, and I can usually arrive at what I need to for the more general formula. Okay, that was our blazingly fast review of trigonometry. I obviously did not cover an entire semester of pre-calculus in the however long that just took. Couldn't have been very long. But I covered the stuff that we're going to need right away. There's some more stuff that you'll need maybe next semester. In particular, all of those elementary trig functions can also be defined in terms of right triangles. We don't need that right now, but very soon we're going to need much of what we just saw. All right. There is a homework on the trig review just to make sure that you're got this stuff under control, so give that a try. Have fun with it as usual, See you soon.